Hey everyone, thanks for coming to my talk today. I'm Mike Shi. I'm the co-founder of HyperDX, and I currently lead the observability product here at ClickHouse. Today, I'm here to share about how we built ClickStack, the open source OTel native observability stack that I've been working with my team on for the last few years. So before diving into ClickStack itself, I want to make sure everyone's on the same page about ClickHouse. This is really at the core of what we've built. ClickHouse is a columnar database that started life back in 2009, went into production in 2012, and has been open source since 2016. Fast forward today, it's ranked as the #1 analytical database on DB engines. And it was originally designed for clickstream traffic, and it's optimized for aggregating and filtering over large amounts of immutable data. And it turns out those traits are pretty dang useful for observability as well. And a brief intro on ClickStack. ClickStack is the open source ClickHouse observability stack. It's an opinionated, easy to use end-to-end stack meant for handling everything from real user monitoring, session replay to the usual logs, metrics, and traces. It's composed of 3 components: OpenTelemetry for collecting data, ClickHouse for the telemetry store, and HyperDX for the querying and observability experience layer on top. All the components are open source, and they're also OpenTelemetry native, and the whole stack is super easy to get spun up in just a few minutes. Today, I'm going to talk about our journey in building this observability stack. And one of the key decisions in any observability stack is where to put all this data, as the data store fundamentally limits the scale and types of problems you can answer. And for that, I want to rewind the clock briefly to talk about some of the prior observability tools. And I really want to start from the humble breadth. That's where I would call kind of like the first observability tool, where you can just go in, SSH into any server, search the logs on any individual machine. And over time, though, we got more and more machines, and we needed a way to kind of centralize all the logs into a single place because we couldn't just SSH everywhere anymore. There's just kind of too many machines to make that feasible over time. So that's when Splunk was introduced. And evolving further, we got more and more machines and more scale with our logs, and to make it easier to collect all that data, Elastic is introduced as a search database as volumes continue to grow. And we eventually expanded beyond the point of looking for error messages for like a specific error message or searching for something specific. We got to the point where we needed to do analytics. We need to find trends and understanding of how data points were behaving over time. And that's where metrics databases work more. They're really good at doing aggregations. And started off with Graphite, which is great for lower cardinality metrics. As we moved to the cloud and became more cloud native, and things dynamically scaled a lot more, and the cardinality increased further, Prometheus was introduced, and then later on Thanos to continue handling the increased amount of volume and cardinality when it comes to metrics. And basically the trend has been over time, volume and cardinality continue to increase, and more new data stores needed to be introduced to kind of fill the issue of scaling to that new challenge. But there was always kind of challenges with these data stores. So starting with the search engine, they're really great at searching individual needle in the haystack kind of problems, but they really have a few shortcomings. One of which is that they're really not optimizing for frequent writes. So they're really great for searching, but not really great for writing. And the other big problem is that they're not fantastic when you need to do aggregates, when you need to figure out, hey, how is this error trending message over time? It's a lot more poor at solving those kind of problems, which is kind of why we introduced a time series database. Time series databases are really fantastic at doing aggregation. They're really great at finding how many errors have we had in the last hour, how many have we had in the last 7 days, for example. Can we break that down by region? So there's kind of the ability to capture these pre-aggregated metrics and be able to chart them over a longer time duration. However, because they're pre-aggregated, we lose the original event that caused that metric. So we can't find, for example, the individual metric, the individual error message that caused that error count to go up by 1. We can't do that way ahead of time. So you get great aggregations, but no ability to root cause. So what if there was this data store that didn't have to make us do this trade-off, where we could kind of store everything in a single place? It would have these really great lightweight indexes, for really fast searches. It still is high performant on aggregations, even on really high cardinality data, that's going to continue to grow over time. And of course, being cloud native, it'd be really fantastic to also utilize object storage as a source of cheap and infinite storage for all the telemetry that our users would want to send us. And actually, there were a lot of properties we were looking for in an ideal observability store. And I highlighted just a few of them. As we mentioned before, one thing that's really important is resource efficiency. So the ability to handle petabytes of data, compress it really well so that we don't have to spend a lot of money on storage and disks and whatnot. And it has to be something that is also tested at petabyte scale so that we know, it's something reliable, that we know we don't have to fight the database to make it work at large enterprise scales. I mentioned before, fast aggregations is really important so that we can build trends and understand analysis of the data over a broader time range, as opposed to just be able to look at a very specific event or just be able to see the trends without zooming into a specific event. When you want to draw the connection between the two, we want a really expressive query language that we're not limited by the database's query language to what kind of questions we can answer for our users. Obviously, kind of going into modern observability, a lot of it is about having structured logging, structured events, wide events of things that are JSON-like, key value-like, so that users can easily, group by a specific property like region or user ID or some other structured information. And also still flexible enough, though, to be able to schema on read. So if someone has given you unstructured log, you're able to still help the user be able to extract out information and then use that in an intelligent way. And then kind of talked about object storage support. And as an open source product, it's also really important that the underlying data store is open source as well, which gives us a ton of flexibility in terms of how our users can use the platform at the end of the day. And we looked around in terms of trying to see what are some of the other folks in the industry doing. And we saw companies like Netflix and Anthropic all adopt a columnar database for their next generation observability platform. And specifically for them, they chose ClickHouse. But in general, when you dig into columnar databases, it's really clear why they've been chosen as a really good data store for observability workloads. So let's dive a bit into columnar databases, what they're about, and why these seem to be really, really good for observability. Now, before, of course, going into why it works really well, the first thing is to probably talk about what is a columnar database for those that might not be super familiar with it. The easiest way to really understand it is to contrast it to its cousin, per se, the row-based storage databases such as Postgres, for example. So instead of storing entire rows together, like you get in a row-based database where we have, every column is kind of co-located each other, row by row. Instead, we want to have a columnar storage. So each column is grouped together. So a file will be all the values of a given column, and of course, row by row be broken down within that column file. And this makes it so it's a lot more efficient to pull out the information we need for a given query. You don't have to read the whole row. We can just read a specific column. And the other thing that we could do as well is that we could also apply ordering on top of this data. And when you apply ordering on top of this data, it allows you to improve the compressibility of this data as well. So you could do things like, for example, delta encoding. So instead of storing the entire value, we could store the differences between neighboring values within a given column. And this allows us to shrink the amount of data we need to store by quite a bit. And then also you can combine it with traditional compression algorithms like CSTD, which allows you to compress data really effectively, especially when they're sorted in a manner where all similar values are grouped together. So those compression algorithms work a lot better when the data is sorted together as well. And as mentioned, because these columns are kind of stored together, all the values in a column are stored together. When you're only reading subset of a column, for example, you're only reading one property or a few properties out of your observability query, for example, you only need to read a subset of the total data size, which allows you to pull out the data a lot faster by reducing the amount of I/O needed to actually do a query. And additionally, on top of this, because it is grouped into columns and all the values of a similar type are together in a same file, we could also parallelize a lot of this information. So we could vectorize it, which allows us to basically process multiple rows of data at once within a CPU. So you're able to do basically process data in batch as opposed to individually at a time at the CPU level. And this kind of parallelization process continues to scale not only at a given node level, but also, at the processor level, but also at the node level. So you can have multiple ClickHouse instances or a database instance work together to be able to complete a given query and pool their resources together. At the end of the day, that just means you get a ton of performance really, really quickly. Now, another kind of great property of these columnar databases is a concept of a sparse primary index. What I mean by this is that in a traditional database, you might have an index that points towards every single row within the given database. Here, with a sparse primary index, we actually don't want to create an index that points towards every single row, but rather, in this case, we might want to point towards every nth row. In this case, it's 8,000, around 8,000 rows. That's just kind of the default 8,192. That's kind of default picked within ClickHouse. That is tunable, of course. But instead of having to basically point towards every single one, we only point to every 8,000, and thus allows us to create indexes that are only in the megabytes of size, even though the original data set might be in the petabytes. It allows you to store a very lightweight primary key, but it's still quite performant at the end of the day, even with a sparse primary key. And the way that this can work is because the data is ordered. So we know that, for example, the first row of every 8,000 rows is always going to be the smallest value of the next 8,000 rows. And using that, we can still kind of use it as an effective primary key. And we can exploit this because when we start doing a query on, for example, a range of data or on a specific value, we could actually just look at the example values within the primary index, so within the sparse primary index, check out which index or which kind of like top row might match this condition. And then if there's a possible match, we'll actually pull out that block of 8,000 and then do a more fine-grained match on top of it. So we can basically eliminate whole swaths of 8,000 rows at a time by just inspecting a single entry within the primary key. There's also all sorts of really awesome other ways and knobs to be able to tune the compute and storage trade-offs and insert and read time trade-offs within these databases, but there is not a ton of time, so I'll just skip in order of the interest of time, but safe to say there's actually a lot more to it than just sparse primary keys. Another really important environment is the ability to handle wide structured events. There's a really neat concept within ClickHouse. It's called the JSON data type. There's kind of other ways of doing it within other columnar databases, but effectively allows us to store semi-structured, like JSON type kind of data within a columnar database. Historically, columnar databases were not really good at this workload because you had to define the columns or kind of like the properties that you care about ahead of time. And this would be, impossible if your developers can just add logs all the time. Then you have to keep the schema being changed all the time. It's very difficult to manage that way. Here within ClickHouse, we have the concept of a JSON type. And this allows us so that every time we see a new property, we will actually dynamically create a column if it's a very common property. And that way, we'll actually store really common properties as a dedicated column, so it's able to be really effective and fast during searching. And then for the long tail, or the long tail of properties where it might be too expensive to turn into a column because it doesn't happen that often, they kind of get put into their own set of shared data. In that case, this allows us to support wide events without having to worry about a ton of schema management under the hood. And still, of course, retain the performance benefits I talked about a lot earlier in terms of why columnar has kind of vectorization and other kind of performance benefits. And one of the things that is also really useful as well is that because columnar databases are usually strongly typed, we don't have to infer a type and get stuck with that type. In this case, we actually keep track of the specific type of a specific property. And so therefore, even if you have, for example, a naming collision between a different property, or basically the same property has multiple different types of data stored in it, those don't get overwritten or it doesn't crash or anything like that, or error out when you try to insert it. We'll just kind of bin it into its own type. And this also allows the database to be really effective in reading the data out, because we'll know, for example, oh, it's going to be all integers. So we actually just pull out all integers without having to do extra type casting on top of it. And of course, also improves compression when there's a lot more uniformity in terms of the types of data being stored in each specific subcolumn there for the data type. And finally, one of the last pieces of this is object storage and compatibility on top of it. And columnar stores are really a natural fit, because columnar data stores usually kind of have a assumption of immutable data or immutable columnar parts. That means you kind of just upload new data as an immutable block into your columnar data, and then into your columnar data database, which will store it into an object store. And once it's kind of an object storage, you could run compute nodes on top of it to query on top of it. So you don't actually have to create a copy on every single node locally. Instead, every node can just read from a shared set of object storage. This allows us to take advantage of really low cost, long-term retention, while also kind of preserving the ability to actually scale infinitely as well. And also it allows us to create kind of really cool ability to isolate compute and kind of like, spend certain compute nodes on certain tasks and other computes on other tasks if you want. So we kind of get scalability, cost efficiency, and flexibility, all from pairing columnar stores with object storage. So just for a really quick recap in terms of why columnar stores work really well for observability, one of them is, of course, cost efficiency and scalability. The ability to do fast aggregation, as we covered, with the ability to parallelize on top of the data really easily, as well as really selective filtering from the sparse primary keys that we cover. And additionally, there's also other ways of creating secondary indices that makes it really quick to be able to skip other swaths of data as well. And then it's also incredibly flexible, so you could both define schema on write with things like the JSON data type, and schema on read, where you get a lot of powerful SQL functions to parse the data, even if it didn't come structured and parsed to begin with. And speaking of SQL, SQL is an incredibly expressive language with tons of rich analytical functions, flexible filtering, and it's a foundation that almost any engineering team is already familiar with. So it gives us the ability to know that the database is able to answer almost any question a user might throw at it. Now, the second part of why adopt OpenTelemetry for the stack. So at this point, I think it's pretty safe to say OpenTelemetry is effectively the industry standard for collecting observability data. It gives us a consistent way of handling logs, metrics, and traces without having to reinvent the wheel. So while the decision itself was pretty simple, and I think especially these days, I think it's kind of really straightforward and almost a no-brainer, it was really fundamental in terms of how we design ClickStack. OpenTelemetry gives us a really rich ecosystem of SDKs across any language, makes it super easy for almost anyone to come from an app in any language to say, like, yes, we absolutely can help you instrument your application, send telemetry into ClickStack. And the other thing is, of course, as an open source company, it's really important for us to practice what we preach, where we're adopting a platform that doesn't encourage lock-in and doesn't have any proprietary agents that you can move off of. And on top of that, the community was a huge factor as well. It just means that it's incredibly fast growing. There's a lot of community support around it, and there's an ecosystem that we can contribute and support on top of that as well. And while we embrace OpenTelemetry really early on, we also recognize that not all teams might be adopting OpenTelemetry. So that means like we're not only OpenTelemetry, even though we'd certainly definitely advocate for using OpenTelemetry a lot and going OpenTelemetry native. We support kind of really any type of wide event or kind of structured telemetry. More or less, we kind of minimally expect just a timestamp and some payloads associated with it. And then on top of that, we can build an observability experience. So it's quite flexible beyond even open-telemetry. So no matter what kind of way you're collecting data, usually you'll have a timestamp and some data associated with it, and then we can build an observability experience on top pretty easily. And then the third part is the platform on top, the developer experience we are delivering for the end users. So the reason that we wanted to build a dedicated interface really came down to the usability for the user. There's other alternatives we could have explored. For example, we could have adopted something like Grafana, which definitely a lot of folks use, extremely powerful, but it still puts a lot of burden on the users to write SQL at the end of the day. And we didn't think that was realistic for everyday developers. Thinking about, hey, if you're waking up at 2 a.m., debugging an incident, really like the last thing you want to try to remember is probably SQL. It's fantastic for really deep data analysis. It's incredibly flexible, incredibly powerful of a language. But at the same time, it could definitely be a bit verbose at times. It can also be a bit tricky at times because how you write the query really affects how the query will ultimately get executed on top of the database. And there's a lot of nuances that can be hard to remember in optimizing the query on top of any database that you run. So while we knew that SQL is a fantastic foundation to both build an application on top of and expose the user if they need it, we also felt that we needed a experience that kind of gave a more purpose-built for observability kind of experience, something that might be more familiar to engineers on a day-to-day basis without needing to require them to know SQL. So one of the heavy investments in our early days is supporting a Lucene-like syntax. So this way, a user can go in and just start type the word error, hit enter, and get all of the events associated with the word error, or they could do property : value, like user : blah, or whatever, and they'll get the users that they're looking for. It's not a new language they have to learn, and it's literally what you already use if you're using Google. Exactly, pretty much the same syntax there. And on top of this, we also invested in things like an English explainer. So while we created support for Lucene-like syntax, which basically takes the search query, we translate it into SQL by parsing it, and then understand the schema, and then generating the correct schema SQL query on top of it. We also created something we call the English explainer, which will translate your Lucene query into a human-readable format. So basically kind of giving you an insight into the AST that we parse out. And this really helps users understand, when I type in this specific syntax, what is the machine or what is the parser actually understanding? How is it going to translate that into SQL? So it gives users a bit more of an understanding of what the query is doing. And then, even if that isn't helpful enough, we kind of have the UI filters you see on the left-hand side that, again, is populated by inspecting the underlying schema that we're running on top of. And we build kind of the classic, checkbox UI filters so we go in and just click on the specific values you're interested in filtering on top of. And lastly, kind of as I mentioned, SQL is incredibly powerful. And one thing we wanted to expose to users was actually the full power of SQL. So you don't have to use the Lucene syntax. If you have a really complex query, if you want to do some specific functions and whatnot, you can actually open the SQL mode of the editor and just kind of write your queries in there directly. And kind of really similarly for charting, we expose a simple kind of like chart building interface, really abstracts away the SQL, and it's really focused more on the specific observability parts for building a chart. For example, picking your aggregation function, like do you want 99th percentile, 95th percentile, without having to actually know kind of the underlying functions and syntax to pull out that specific aggregation. And beyond that, there's a lot of happy paths when it comes to matching the schema to the query that the user is building. So one of the things that we want to do as well is we kind of want to encourage users to kind of like fall in the pit of success in terms of building a query that matches the way that the underlying data is stored and optimized for. So in this case, we kind of make defaults, kind of like the easy path, the path that will get you the most optimized query. So for example, by default, we'll do a token search when you put in a given word. So we're going to search a whole word, which we can really easily accelerate via a secondary index. on top of your table, and our English explainer will tell you a batch of call words while also kind of giving you an escape hatch for doing substring searches. And then we do other things as well, such as, for example, prioritizing filters that would have a better impact on performance near the top of the list, so that you're hopefully a bit more encouraged to prioritize looking at those filters, selecting some values, which will help kind of like scope down the data more effectively for a given search to make them even faster. And then on top of that, there's a ton of small optimizations that makes the experience really, really good for our users. And this is the part where you really want to have like a deep understanding of the data store that you're running on to really maximize the performance you can get out of it. So for example, the interface isn't just a pretty layer on top. It has to be aware of how the data is structured. I've already kind of been mentioning how we kind of look at the schema before generating the queries. And there's a lot of ways that we do that. So for instance, we are able to analyze the underlying primary key of the index that's in place of the table, and we can selectively apply optimization to the query based on how that key was being structured. For example, if your key is structured in a way that allows us to do chronological ordering, we'll actually have ClickHouse try to read that data in chronological order, but biasing towards either the newest or oldest data, depending on the user preference, so that we're able to get the results back as quickly as possible. Basically, as soon as ClickHouse sees a new result, it will return it back to the user, as opposed to waiting for the entire kind of search to finish and then returning the response in bulk. And that kind of speeds up the time to the first result. Another example is really the ability to also like chunk queries or window queries into smaller queries. So for example, you might be looking over a really long time range, but maybe all of the matches will actually happen pretty near the beginning of the search window or the start of the search window, whichever direction you're searching. So in this case, it's actually a lot more efficient to tell ClickHouse to give it many smaller windows of queries, kind of prioritizing the ones that are more towards the beginning rather than the end. And that way, if we load enough data from some of the beginning queries, we can actually cancel the old queries. And this allows ClickHouse to we're basically telling the underlying database to focus on a specific subset of data, the more recent ones, as opposed to the older data, and kind of spend all your compute, IO, and bandwidth there. So to wrap this up, when we built ClickStack, we made a foundational decision to use a column-oriented store. And this decision actually came before when we worked on the HyperDX. That's kind of the origin of all this. And it's one that we continue to believe that was the right one, and that we think that columnar databases indeed are the foundation for the future of observability. A lot of different tools, not only us, are built on top of columnar databases. At this point, whether it's ClickHouse or other columnar databases, they're definitely kind of really well positioned to continue taking over these types of workloads. They're usually kind of SQL based, which makes them super powerful and flexible, and also really easy to build on top of, and easy for other engineers to learn, since they're probably using SQL somewhere else, like a Postgres database for the application. And of course, the part that we spend a lot of time on is that building the user interface on top can be really tricky. It's not just a fancy UI. It's not just kind of something you can just vibe code that outputs some generic SQL. Really, you have to understand the nuts and bolts and kind of like the query plan and how the optimizer works under the hood, and how the disk file layout on disk, for us to make sure we're always generating the most efficient queries for the user. We're really kind of allowing users to find the most success by biasing them towards using the most efficient queries possible. And that's pretty much it for my talk today. Thanks so much for taking a look. You could try out the public demo. We have a no login public demo. You can check out with the QR code on the left. And if you're ever interested in using ClickStack as well, you can get started with the QR code on the right. Otherwise, thanks again so much. Hopefully you guys get a chance to check out some of the work we've worked on as well.